Welcome everyone to the 2DCC webinar here on March 24th. Today we have Dr. Deep Jariwala from University of Pennsylvania. He is Assistant Professor of Electrical and Systems Engineering and also Materials Science and Engineering. Today he'll give a talk on photovoltaics with Waals Semiconductors, promising or pipe dream. Handing it over to you, Dr. Jariwala.
All right. Well, thank you, Eric, Kevin, Joe, and everyone for inviting me and giving me this opportunity. And thanks to everyone for attending. I hope all of you are keeping safe and healthy inside your shelters. Let me get started with this talk or webinar. And what I would like to focus today is on photovoltaic Waals semiconductors. And I've been been working in this area for some time, and this is probably the first time that I'm giving this kind of a long talk on just photovoltaics to make it more like a tutorial type talk. So what I want to get across in this talk is not just my own results, but also sort of how do we look at this field of this more very novel semiconductor materials, and how do they fit with the photovoltaic application, and what are sort of the prospects both in terms of practical applications as well as basic science for these materials in this application domain, which is photovoltaics or light harvesting moving forward. So I'm going to be a little bit shameless and do a little bit of self-promotion of my own lab at the beginning, and that my lab is sort of divided into broadly 4 areas, and one of these areas is sort of nano-electronic or purely electronic devices where we don't shine any light, and we work on memory devices, tunneling FETs, the triode devices, and of course regular field effect transistors in this part of the group. And of course most of our devices include some kind of 2D semiconductor, and we've recently started having some work published out in this area, especially just yesterday. We had our first paper in this area sort of come out in Nano Letters. Feel free to take a look at it. Of course, the other area that we work on is nanophotonics, which is the fundamental photonic phenomena as well as applied phenomena such as photovoltaics. And this is what I'll be focusing most of my talk on today. I will mention a little bit about how fundamental nanophotonics can feed into some of the interesting perspectives on photovoltaics with 2D semiconductors. And we also look a little bit into near field scanning probe microscopy coupled with optical spectroscopy, such as the tip-enhanced Raman and tip-enhanced photoluminescence, as well as we have some presence in the area of in situ electron beam microspectroscopy. This is mainly in collaboration with Eric Stack here at Penn. And we also have some efforts in growth and synthesis. Of course, it is a very small effort compared to what 2DCC has, and we're not even close over there, but hopefully we'll be having some interesting results to share on that front in the coming years. So as I said, I'll be focusing most of my talk on the photovoltaic devices out of 2-dimensional semiconductors. Maybe at another day or next year or something like that, I'll be happy to give a separate webinar on nanoelectronics and future prospects of 2D semiconductors in that domain. So what I would like to get started with is assuming that most of the people attending know very well about 2D materials and 2D semiconductors, but maybe not everyone is familiar with the application of photovoltaics, and of course and where that field is. And I think it is very easy to see that photovoltaics or solar energy is sort of the dominant source of energy available, which is not very well harvested. And I think this one sentence just makes the case for me, which is 90 minutes of sunshine is roughly equal to annual global energy consumption of all of humankind, right? And so all you need is a very small fraction of the incident solar power every day to be harvested to basically fulfill our energy needs for time, for indefinitely, roughly. So with that said, I believe everyone would also know that modern photovoltaic technology is dominated by silicon, just like modern microelectronics is 99% silicon. Modern photovoltaics is also, I would say, definitely more than 95% silicon, right? And the reason silicon is dominant is because we have figured out how to produce large area and very high quality of single crystal silicon. And we have learned our lessons very well from microelectronics, and all the know-how that we had in microelectronics, we have transferred it to making very high quality and cheap silicon for photovoltaics. And this has resulted in tremendous gains in terms of improving efficiency and also sort of lowering down the cost, which is the most critical component. And I will touch upon a little bit onto why cost is very important, is because if you want to sort of have a mass market technology, this is what really matters for photovoltaics, right? If you, in fact, believe any of the data coming out of US Energy Information Administration, as well as what DOE has been saying for a while, is that if you look at solar PV, just the economies of scale as it kicks in, the price is going to keep falling such that it is going to become cost competitive with natural gas as well as coal, which are non-renewable energy sources. And this was prediction made in 2015 for 2020. And if you look at the more recent one, I was presenting this data a few months ago and somebody said that this data is old. So I looked up new data, and on the right-hand side, now I have newer data, again from US EIA, where in terms of 2019 dollars per megawatt hour, once again, for different regions, natural gas versus onshore wind versus solar photovoltaics have been compared. And these predictions are for 2022, 2025, 2040. And you can clearly see that solar photovoltaic is sort of becoming competitive, right, with these other technologies, especially natural gas, which is non-renewable. It's a fossil fuel, so it's sort of important over there. And so, all this is mainly because the price of silicon photovoltaics has fallen tremendously, while the efficiencies have also remained consistently high, even while scaling up. And so this begs the question, right, that why would any of the researchers doing research in novel materials for solar energy should be doing research, right? I mean, from a sheer economic perspective, the problem is solved. You just keep scaling silicon up further and further, and you will be able to address everything. But I'm going to pull up this ugly looking chart of NREL that everyone who gives us photovoltaic presentation gives you. There are many new materials and technologies where people have been doing photovoltaic research, and there must be some reason behind it, and we'll get to some of those reasons soon. But beyond silicon, of course, there are 3-5 semiconductors, and they've also been known for a long time. And of course, there are many thin film and emerging PV technologies. And the sort of key metric to understand over here is that for a large scale commercial application, this unit matters, dollars per megawatt hour. In other words, you want your technology to be as cheap as possible, or your cells to be as cheap as possible, and they should be as efficient as possible. Only then you can minimize this metric, right? And so if you look at this chart, yes, there are a lot of very promising technologies. Many of them are much more efficient than silicon, especially the double junction and the 3-5 semiconductors. Are they cheaper than silicon? No. So therefore, it doesn't quite fly. Then the question comes of more of emerging technology, and some of them have been there for a very long time, such as organic photovoltaics. One of the main reasons why perovskite photovoltaics is becoming so popular and they are being considered serious candidates is because not only they are cheap, but they can reach efficiencies comparable to that of silicon, and therefore you can now start making a case for them, right?
Dr. Jariwala, we have a question that's pertinent right now. The question is, why photovoltaics?
Again, I can't get the context of the question just from 2 words, but I'm trying to get there. Hello?
Go ahead.
Okay, all right, yeah. Okay, so the point I was trying to make is that if you want to then look at 2-dimensional semiconductors, there is sort of an interesting comparison to make over here in terms of both efficiencies as well as pricing, right? I mean, with the chalcogenide semiconductors that everybody would be familiar with, they would be as expensive to make or grow or scale up over large areas as, say, the 3-5 or compound semiconductors. Whereas on the other hand, their efficiencies are nowhere close, as you will see in this talk. And so they don't really lie in this picture of being cost competitive or efficiency competitive with any of the known technologies, let alone silicon. And so it's really hard to make a case for them in terms of terrestrial commercial solar power. But you could make a case for them for other types of photovoltaic applications. Photovoltaic applications or energy harvesting applications where silicon or all of the other known technologies have certain disadvantages, such as they cannot be flexible. Silicon in particular cannot be very flexible. And therefore it is more difficult to implant. For example, also in applications where weight is very important, silicon can be really heavy, and I'll get to that very soon. There will be it will be a real challenge to employ silicon-based cells. Of course, then there are technologies such as organic PVs and polymer PVs, which can be more flexible, but they have their own disadvantages in that they have lifetime and humidity and degradation issues. So, okay. So what I want to get to the point is that there are some applications where you could have you could do away with bulk silicon or 3-5 semiconductors, and here some of the novel semiconductors could have a real advantage. But then the argument could be made is that it's a very small and niche market. Do you get anything valuable out of them? And so towards that line, we have been looking at a more sort of out there technology, which is space-based solar power. And when I talk about space-based solar power, I'm not talking about powering the International Space Station or a satellite, but actually looking at putting square kilometer arrays of solar cells in space, harvesting or harnessing the solar energy, and then beaming it out back to Earth in the millimeter wave radiation atmospheric transparency window, such that it can be received by an antenna on the ground and can be stored in say batteries or directly transmitted. And then there are several advantages of such a technology. Of course, this is not a new concept. This is known for many years. In fact, there were Russians who had predicted this back in the 70s. You could do something like this. The main advantages over here is, of course, you have higher solar flux out in the upper space. There is, of course, no nighttime if you put it in the right orbit. And believe it or not, if you use the atmospheric transparency window to transmit the electromagnetic energy down back to Earth, it's actually way more efficient than putting transmission lines. So for example, if you wanted to transfer your energy into a remote location, say for example, a hurricane hit one of the islands like it happened in Puerto Rico, and the entire grid sort of dies down. And if you just had antennas to sort of receive this power, you can beam the power remotely to any location. Likewise, for say military applications, where in remote locations you don't have a grid and you want to directly beam power to them, for something like that, a space-based technology which can, by use of phased arrays, you can direct the power where you want, can be quite beneficial. So this is what we have been primarily looking at from this particular application. And of course, there are companies as well as people in the defense agencies that are quite interested in something like this. And so if you want to consider anything which is up in space, the critical thing, or even for aerospace applications or airplane applications, the weight becomes certainly very important, because one of the most expensive components of shipping something up in space is actually the shipping cost, right? And so for such an application, you can do away with a very low efficiency solar cell, but what you do not want is actually a heavy solar cell. Okay, and so the key metric over here is power per weight. And if you want to compare the power per weight for all your favorite technologies of solar cells, you can plot them the way I've shown on this plot, and you'll quickly see that all you have to do is take the word ultrathin and keep inserting it in front of your favorite technology, and you can go up by orders of magnitude on this logarithmic scale over here. And so if you want to think or have some sense of comparison over here, you'll notice that even for some of the thinnest organic or perovskite technologies, the active layer thicknesses in them are still pretty large. It's a few hundred nanometers, so to speak. So they're still pretty thick cells. And so we wanted to think about, as well as I think the community wants to think about, are there materials that can push these limits even further down, right? Down to 10 nanometer limit, 1 nanometer limit. Can you do it? And I'm going to make some arguments where you'll see that, some of the 2D semiconductors are pretty much the only known candidates that have all these properties together. Okay, and so a good part of my talk would be also be taking cues from this perspective that we published 2-3 years ago now, where we have this is sort of different than most review articles. It's sort of a more forward-looking perspective where we have done a bunch of calculations and sort of projected what are the things that you would really need to do in order to make van der Waals semiconductors to be viable photovoltaics, right? So feel free to look it up, and you will find that many of the figures I've used are taken from this article. And so the real the challenge for us when we started thinking about this was that, can you take the bulk solar cells that you would normally put in space and thin them down to an atomically thin solar cell while maintaining some kind of efficiency? I mean, you don't want the efficiency to be completely close to zero. I mean, it has to have a decent efficiency, and then it has to be very thin in order for the ratio or power per weight ratio to go up. And so the question that we had was, can you efficiently trap and harvest light in atomically thin semiconductors? So again, this is a community that would know very well about atomically thin semiconductors, so I don't want to go into too much detail about introducing the materials themselves, but I'm talking about transition metal dichalcogenides of moly and tungsten. That is what I'm going to focus most of the talk on. Of course, I'll give out some hints about what other materials might also come into play or picture and function as very good 2D semiconductors photovoltaics moving forward. And so what I want to do is sort of go back into the past and sort of see when did people actually started or start thinking about MOS2, WS2 and the like as photovoltaic materials. And this was way before I was born. In 1981, there were people in the University of Ottawa, Fortin and Sears, who were trying to use MOS2 for photovoltaic, and they reported photovoltaic effect and optical absorption in it. And they were able to see some very nice photo response. And what they had essentially made was some kind of Schottky junction solar cells of various metal contacts made on top of bulk MOS2 crystals. And then they did some temperature dependent measurements where they measured the open circuit voltage and short circuit current of the photovoltaic. And then they were able to see some values. Their best cells were basically copper moly disulfide Schottky junction cells, and they had about 1% efficiency at 120 Kelvin. So they were not very good cells, obviously. But what caught my eye was this very last sentence in the paper, is that MOS2 is expected to be a suitable material for photovoltaic solar cells because of its direct band gap, well situated at 1.8 eV, its wide spectral range of photo response made possible by a favorable distribution of absorption coefficient value, and its easy availability. Okay, now, they were obviously from Canada, and Canada has the giant deposits of MOS2 in the ground, so maybe it was easily available at the time. I guess most of our bulk crystals early on in the community also came from mined, which were directly mined from the ground. So it's certainly possible. And what is the last sentence, which says over here that it's quite possible that higher efficiency at more convenient temperatures will be obtained following a more determined effort to produce MOS2-based solar cells. So it's quite a nice outlook over here. And back in 1980s itself, somebody had thought about this, and what they had identified nominally was that the absorption was in the right range and the band gap was in the right range, which is sort of important for this. Now fast forward about 30 years or so, and then when the field of two-dimensional semiconductors erupted, people started making all kinds of photo detector and photovoltaic devices out of them from exfoliated or scotch tape exfoliated flakes again. And these are some of the earliest reports over here where Paula Barbara back in 2013 demonstrated, again with a very similar concept, just Schottky junction, but now we have asymmetric Schottky junctions, or in other words, one ohmic and one Schottky contact. And so you can use these asymmetric metals such as gold and palladium, shine light on it, and you do end up seeing some photovoltaic effect. So that there you go. They can be used as photovoltaic semiconductors. We went on right after that in the same year, and this was back when I was doing my PhD. We proved that this effect is mainly localized at the contact because of the Schottky junction, and that it is indeed photovoltaic in nature, because as you apply the bias, you can kill the photovoltage or photocurrent at the contact. So certainly it was true. Now, after that, of course, there was an explosion in the amount of research on optoelectronic devices, broadly speaking, from 2D semiconductors. And if you look at the photodetector plus photovoltaic research in this community, it can be sort of divided into a few sections. I'm highlighting a couple over here, which are basically in-plane junctions and out-of-plane junctions. As we'll get to very quickly in the structure of a solar cell, you need some kind of a PN junction to basically get photovoltage out, and you can make these PN junctions in plane or you can make them out of plane. Of course, the 2DCC center and the community knows about making these junctions very, very well. And of course, then you can have homo junctions versus hetero junctions, and people have looked at a few ways of making hetero junctions and a few ways of making homo junctions. Because they are atomically thin in nature, you can use electrostatic doping to also make homo junctions, or you can actually use substitutional doping. For hetero junctions, again, people have tried different techniques, growing one on top of the other or stacking one on top of the other, which is what we do, as well as making hetero junctions with other 3D semiconductors, such as silicon or gallium arsenide or indium phosphide. And some people have also tried to do selective doping of the few top layers into p-type of naturally n-type occurring crystals to make these vertical homo junctions. So again, I don't want to offend anyone over here. There is a large amount of research that has been done in this area. I cannot possibly cover each and every piece of literature that people have sort of put out there, but I'm going to highlight some to sort of show you sort of the spread of what kind of researches people have done in showing or the early research on photovoltaics from 2D semiconductors. Of course, there was this early work again in 2013 about sandwiching a TMD, say WS2 or WSE2, between two sandwiches of graphene, and one graphene was more highly doped than the other. So this was again, in some sense, an asymmetric PN junction, which was showing photovoltaic effect. As I mentioned on the previous slide, people have also used split gates, and by using a split gate on an intrinsic semiconductor, you can induce one side to be P and other side to be N, depending on the gate bias you apply on either of the split gate, and then you can generate a photovoltaic effect. Likewise, people have found that you can have type 2 junctions formed between MOS2 and WSE2, two of the most popular combinations, and when you stack them vertically, you can get a photovoltaic effect. Likewise, people have tried to grow them laterally or stitch them in plane, and people have also observed photovoltaic effect in that. So there has also been a lot of work in that area. And finally, there are a lot of work has been also focused on integrating MOS2 or other chalcogenides directly with silicon or gallium arsenide or indium phosphide. What has been unclear, and even organic semiconductors and quantum dots, but what has been unclear over here is in most cases, it is unknown how much of the efficiency actually comes from the silicon or 3,5 or the organic component as opposed to MOS2. Overall, broadly speaking, I would say that most of these devices are sort of proof of concept demonstration. There is like no there's like no useful efficiency over there. Most of them have efficiencies in the 1% or sub 1% range. And many of these devices are just proof of concept that you can see a photovoltaic effect. This includes all the way from the Schottky junctions to these sophisticated split-gated PN junctions, right? And so the real question you want to ask is that if you look from the photovoltaic community's perspective, what other things did you want to do to actually make these semiconductors into useful photovoltaics, right? And again, it feeds back into the application that I was telling you earlier, and how does all of this sort of tie together? And so what I want to get to is, again, give a very brief primer on what are the materials and device design criteria one should consider if you want to really design a high performance photovoltaic, right? And so there are sort of three major criteria that I'll go over, and then I'll explain why some of the 2D semiconductors sort of satisfy a lot of these criteria, right? And first is, of course, light absorption. You want your material to absorb as much light as possible, right? And so if you want to absorb or maximize light absorption, of course, you want your material to have a certain amount of thickness, so you have maximum interaction of the light with the material, right? And then minimize absorption losses. At the same time, you want your, once the light is absorbed, it generates electron-hole pairs, and these electron-hole pairs have to get collected and to get collected, they have to pass through this. They have to pass through the semiconductors into the contacts. And if you want to sort of minimize the losses over there, you want to have your material as pure as possible. But we all know that no material is ever fully pure. There are always defects which can lead to the recombination and therefore loss of light and loss of electrical power. To sort of avoid something like this, you want to minimize the amount of distance that your carriers need to travel. And otherwise, you want, or in other words, you want to sort of reduce this dimension over here. And this has been sort of a challenge, and this is something that is known in silicon as well as 3-5 semiconductor community, and the people have tried to do this by so-called optical or photonic design, where they have tried to minimize the thickness of the semiconductor and then incorporated optical elements such as resonators or mirrors to have the incoming light bounce around inside multiple times and get fully absorbed. Many of these techniques have not paid the rich dividends, because most of the semiconductors this has been tried on are this 3D semiconductors, where such as silicon or gallium arsenide, where as you start reducing the thickness, of course, you are going to increase surface to volume ratio, and all surfaces are basically unpassivated. For 3D semiconductors, there are dangling bonds always, and they lead to massive recombination and reduction in efficiencies. If you don't believe me, just go ahead and try to Google up and see if you find efficient 100 nanometer thick silicon or gallium arsenide or any of these solar cells. You'll see that the efficiencies are below 0.1% for many of these. But there is a clear challenge over there. And so if you just compare these two criteria over here, in one case, you want to maximize light absorption, and in other case, you want to minimize the current degradation, right? And to do both of this is sort of challenging. And I will try to address how that may be possible with some of these atomically thin materials. The final criteria that comes in is, of course, the potential that you generate across your cell. And this depends on the open circuit voltage. And this open circuit voltage is dependent on the band alignment in the p-n junction, or band alignment of the contact along with or metal contact along with the semiconductor. And so there are a few things to look over there. What I will say is that these two the first two criteria sort of go together, and to realize that, you basically want semiconductors that can maintain extremely high electronic and optical quality while being extremely thin. Okay, so even if you reduce the thickness, you don't want the electronic quality to degrade. Or in other words, they should maintain passivated surfaces. And we know this is possible because we know you can make a very nice transistor as well as get very nice PL and other optical properties from even monolayers of transition metal dichalcogenides. So you do maintain very high electronic and optical quality down to monolayers in 2D materials. So this criteria is fulfilled by them, and therefore they become sort of an interesting case study over here. The third one is a more difficult criteria, and this is something that I'll touch upon as we get towards the end of the presentation, that why most of the research would be needed in this direction if you want to make something practical out of that. In fact, to give you a sense, for most practical photovoltaic technologies such as silicon or gallium arsenide or any of the other ones, voltage engineering has been the most daunting challenge. Most of the research in the more mature photovoltaic technologies is focused around optimizing more voltage rather than light trapping or current collection. Okay, so going back to the first property, which is absorption, how do transition metal dichalcogenides compare to other photovoltaic technologies? Well, the good news is that they really have very high absorption coefficients, right? They are some of the highest absorption coefficient semiconductors known, more than organics, more than SiGs, 10 times more than gallium arsenide, more than perovskites, 100 times more than silicon, right? So this is quite good. We naturally have very highly absorbing materials, and so certainly they should at least be investigated for photovoltaic applications. The other thing is, of course, the band gap of bulk TMDCs lies in this 1.34, around 1.34 eV, which is the Shockley-Quasier limit or detail balance model, given number, which tells you at what band gap you will have the maximum in sort of power conversion efficiency from the solar spectrum, correct? The other important aspect about the optical constants is that not just they have very high absorption coefficient, which is nothing but the extinction coefficient, or K, in the optical constants, but they also have extremely high refractive index. So the N is also really high. If you look at the N over here, the N values even sub-gap are more than 4, and N is the real part of refractive index, or refractive index as we just call it. So the optical constants are also extraordinarily high. How do these optical constants compare to some of the other materials? Where here they are compared to silicon. You can see that where your WS2 or tungsten disulfide starts absorbing at the exciton over here, K is already 1, whereas where silicon should ideally start absorbing, which is close to 1.1 eV, you see that the K is almost 0, right? So or very close to 0. You can't even see it on this linear scale. And of course, there is this is one of the main difference why tungsten disulfide is sort of 100 times more absorbing than silicon. Even in terms of refractive index, tungsten disulfide has much higher refractive index. And I'm showing you just one example of tungsten disulfide over here. It's sort of similar ballpark for all the major semiconducting TMDCs. Likewise, if you consider for say gallium arsenide, which has a band gap range, which is sort of more comparable to the band gap values of tungsten disulfide, once again you see that the K values of tungsten disulfide is much higher, and N values are also higher, right? And so not only it can absorb more, but N is sort of a measure of how easily you can trap light into it, and so there is a definitive advantage over there as well. Here is some comparison of optical constants, and here first I would like to compare absorption coefficient of the 4 major semiconducting TMDs that most people focus on for optoelectronic applications. And I would like to compare these optical constants to say gallium arsenide or perovskites, which are again very popular and promising, and then silicon. And you can clearly see that the absorption coefficients across the spectrum in the visible part where we really care about are higher than all of these, right? And so this really matters. The other important metric to sort of compare is known as loss tangent. And loss tangent is nothing but the ratio of imaginary part of epsilon or permittivity to the real part of permittivity. And it's a measure of how effectively one can dissipatively trap electromagnetic energy in a medium, or in other words, how well can you sort of make light absorb into this material via any kind of nanophotonic design. So this is sort of the function of loss tangent. And you again see that, compared to silicon, which is nearly close to x-axis over here, the TMDs are much, much higher. And so really they are promising if you want to trap light in them. Okay, so this is what we started out to sort of investigate, that would it be easy to trap light into two-dimensional semiconductors and then think about making a photovoltaic out of them. Now, this idea that the N is high is actually a bane sometimes in terms of light trapping, because if the refractive index is really high, then if you have a bulk crystal such as WSE2, as many of you may know, the crystal is really shiny. It's like graphite. It reflects back most of the light. So even though we hear about this all the time, that a monolayer can absorb 10 to 12% of the light, it's not like 10 layers are going to absorb 100% of the light. In fact, it just saturates out at 40%. And because of the mismatch in refractive index between air and the TMD, the refractive index of TMD is so high that by the time you reach to 10 or 15 layers, it is reflecting back most of the light and not absorbing as much light. And this is why you see your bulk crystals to be shiny like graphite, right? And so for a few nanometers thick TMDCs, you are going to limit your absorption to 10 to 15% if you are very thin, or if you are very thick, you are going to limit it to about 40%, and most of the other light will get reflected or transmitted through, right? And this is what you are stuck with. And so if you really want to trap light into it, you have to start thinking about more creative ways. And I'll talk about it a little bit later of how people have tried various different ways to trap light in TMDCs. But what you want to do is to find a way which is easy to do. If it requires a large amount of micro and nano fabrication, then it's probably going to add to the cost, add to the weight, maybe lead to more defects or residue on top of the material that could kill photovoltaic efficiencies. And therefore, you want to stick to as simple of a technique as possible. Fortunately, because the index is high and absorption coefficient is also high, you can take advantage of just Fabry-Perot, or I would say lossy Fabry-Perot like trapping mechanism, where you can take a mirror-like material, say gold or silver, And we have generalized this in more unpublished results to even like Bragg mirror type structures. And if you just put a TMD layer, a few nanometers thick, on top of this kind of a reflecting substrate, as the light comes in, it already starts undergoing absorption. And as it starts going absorption, there is of course a phase shift as well. And then it gets reflected, and then it tries to come back up. And it comes back up, it has undergone a certain amount of phase shift. And so with the incoming wave, it can undergo a destructive interference and actually get resonantly absorbed into the structure. Again, and even if it is not absorbed, because this mismatch in refractive index is so high, it can again be bounced back inside, and you can have an almost 100% trapping without the need of any nanofabrication. Okay? And this is sort of important. A lot of people have figured out a ways to trap light in all kinds of materials. Most of these things require some kind of etching, patterning, putting on plasmonic resonators, what have you, dielectric resonators. You don't need any of this over here. Just have your film sitting on the substrate, it will do the job. Okay? This was so simple, we almost didn't believe it. Go ahead and try it in the lab. You'll see that if you exfoliate, this is an example of WSE2 on top of a reflecting silver or gold substrate. You'll see that for even very small thicknesses like 13 nanometer, you'll see that it is looking nearly black. Eyeball spectroscopy should tell you that whatever appears black should be absorbing a lot of light. If you don't believe it, go ahead and do some basic transfer matrix calculations, basic solutions to Maxwell's equations in one dimension. And you'll see that if you take the optical constants, which have been measured before by spectroscopic ellipsometry, and calculate how much light is absorbed by thickness varying tungsten disulfide or tungsten diselenide on top of a silver substrate, you will notice that for something as small or as thin as 13 nanometers, you can get nearly 100% absorption. Okay, and this matches really well, both qualitatively and quantitatively with experiments. Now, the quick question that you always get is that how much of this light you're dumping into the metal, because metals have non-zero absorption, versus how much of it is going into the semiconductor. Again, if you're doing the calculation, this is easy to identify how much electromagnetic energy is going in which layer. And if you calculate that, you very quickly find that about 10% of the electromagnetic energy, which is the difference between dashed line and the solid line, is going into the metal. In other words, the dashed line is the amount of electromagnetic energy that is going into the semiconductor, which is about 90% of the total absorption, which is pretty darn good. Okay. It is also worth noting that it sort of occurs for a very sweet spot in thickness. As you start increasing thickness further, this near unity absorption peak starts shifting more red, right? And there is sort of this sweet spot in between where you can get the maximum amount of coverage or area under the curve when this is around 13 to 15 nanometers. So great, you already have sort of half a solar cell. You have your semiconductor, you have one of your electrodes, because your metal, which is gold or silver, can already be used as one of the electrodes. So then, can you go and make a Schottky junction solar cell out of it? Sure, you can. We did it. It works terribly, right? And you know, Schottky junction solar cells are not meant to work great, and definitely this one doesn't work great. But another major reason it doesn't work great is because we made a cell which was something like this, where you had some kind of electrode on the top, then there was another Schottky junction electrode at the bottom, and you were exciting all these carriers over here, and they had to travel all this lateral distance to get collected over here. And so the ideal way to do it is actually not have a Schottky junction, but have some kind of a PN junction. And fortunately, we have 2D semiconductors that have some different kind of doping. I think it would be wrong at this point to say that WSE2 is p-type. I think it is more intrinsic in nature. But the good news is that between MOS2 and WSE2, you have a type 2 junction. If you have a type 2 junction, you have this inbuilt potential which can separate out the carriers. And so if you can do that, and then have a transparent top contact, such as graphene, or maybe some other transparent contact, you can have this vertical carrier collection and really a very thin solar cell. And so this is what we went about and made it. And you know, I'm sure some of you may have seen these results, so I won't be diving too deep into it, and would get to perspective soon, so that so that we can have a discussion on where this is really going. But you can make this very thin PN junction, which is about 9 to 13 nanometers in thickness, with a transparent top electrode and a back reflector, as well as electrode that helps you trap all the light. You can then do what we call as a scanning photocurrent microscopy of this device. This is again just Scotch tape exfoliated and stacked flakes one on top of the other. You can point your laser to any spot over here and sort of take a full spectra. You'll see that if you take a line cut, what you had as a just a Schottky junction like before, where you did not have a top electrode of graphene or a PN junction, the amount of photocurrent coming out is really small. Whereas if you make a PN junction versus graphene, this photocurrent intensity sort of jumps by several fold. And you can go and do a more quantitative measurement over here, where you'll see that the absorption again is really, really high, more than 90%. And the external quantum efficiency is also sort of exceeding 50% in certain parts of the spectrum. And all of this is for 9 nanometer thick active layers. Okay, so I think this is sort of the important thing to remember over here. For these small thicknesses, try and make cells out of most other known materials. You will basically get noise. Okay, try it with organics, try it with silicon, gallium arsenide, what have you. Okay, you basically just get noise. The fact that we are able to get several tens of % in EQs is actually a very significant number for these small thicknesses with vertical sort of carrier transport, which tells you that they're already pretty darn good, but there's a lot more work to be done. Of course, you can go ahead and measure even more details through it, such as if you can do the calculations, you can find out how much of light is going to the semiconductor versus how much of light is being lost in the metal, as well as the top graphene contact. You'll see that gold actually has a lot more loss in it as compared to silver. But if you know how much of it is useful absorption in your active layer, you can go ahead and estimate what is known as an internal quantum efficiency, or IQE. And you'll find that you can have an upper bound of IQE of about 60 to 70%, which is not bad at all. But this also shows you that there is a large gap to cover over here. There is about 30% of electrons being lost somewhere, even when you have this thickness to be really, really thin. We have also observed some more exotic things going on over here, that when you are in the very small thickness regime, such as 9 to 13 nanometers in thickness, your internal quantum efficiency, of course, you measure your external quantum efficiency, which looks like very different spectra. But when you normalize them and get the internal quantum efficiency, you see that the internal quantum efficiency is not very sensitive to a function of thickness. And we don't know what is actually happening over here, but we think some kind of ballistic carrier collection or scattering free carrier collection is happening, which may be a new transport regime for excited carrier collection. And I'll talk a little bit about it towards the end. I would also say that this is still very preliminary, and I think more experiments, and there is room for more exciting experiments in this area moving forward. I'll also say that since 2DCC has made so much progress and exciting work in this area, that you can actually scale this up, right? And this was done in our lab and at Caltech, where using MOCVD, you can now grow films over large areas. Not only you can grow films over large areas, you can also control the thicknesses. And then when you transfer these films of MOS2, WS2, WSE2, what have you, onto gold and silver substrates, you are no longer limited to these Scotch tape-like tiny 10-micron devices, but these are centimeter scale films. And this black or dark blue looking film over here is actually 13 to 15 nanometers in thickness, grown via MOCVD and transferred onto a gold chip or gold silicon chip evaporated with gold or coated with gold. Certainly there is room for scaling this up. The question is, where do we go with this? So the dirty secret is out here. The power conversion efficiency is still not very large. It's about 3 to 4%. Okay, and this is not great. But for the thickness that we have, for a lot of these space-based applications, this may be enough if you just normalize it to the weight. Now the real question is, where do we stand in terms of power conversion efficiency, and how far can you go? Right, and we stand right here, somewhere below 5%. But if you look at the detailed balance model and try to do a calculation of where bulk TMDCs should lie, and I'm saying bulk TMDCs because all of our cells are few layers in thickness, which is essentially electronic bulk, right? And so if you look at their band gaps and compare them, they should be very close to silicon, right? But they are not there. They are somewhere below 5% over here. And so where is all this losses going in? And the real place it is being stuck at is actually the open circuit voltage. So in terms of absorption, we already have a lot of absorption. Carrier collection should not be bad. As I told you, internal quantum efficiency is approaching 70%. Then you should be being limited by voltage. And of course, we are being limited by voltage. In fact, if you look at our open circuit voltage, the open circuit voltage are very low. It's about 0.35 right, EV. And if you look at the band gaps, it's about 1.2 to 1.3 EV. This is open circuit voltage should be on a very good cell should be at least 70 to 80% of the band gap, maybe even more if you are like say gallium arsenide, but it's clearly far from there. And so there's a lot more work to be done in terms of open circuit voltage. We have attempted a little bit to this end, and the obvious thing to do would be if you have a PN junction with some band alignment, either you sort of maximize that band alignment or maximize the built-in potential if you start doping p-type more and n-side more, and therefore the built-in voltage within your diode keeps increasing, and that should not also lead to an increase in your open circuit voltage. Turns out that is very difficult to do for very thin materials, and also if you're going to dope your absorbers heavily, you're also going to create more sort of recombination losses because dopants are going to create defects, right? And so the real way to go about this is use of carrier selective contacts, and this is something that the silicon people have done really well, where you use nearly intrinsic absorbing layer, and then you have wider band gap materials which are heavily doped, such as sort of conducting oxides, for example, where one edge of an n-type conducting oxide is sort of aligned with the conduction band of silicon, and the other edge or valence band of a p-type conducting oxide or any other wider, larger gap conducting material, where the valence band is sort of aligned to the holes. And in that case, basically, if your material is thin enough, your excitons or carriers are always going to reach a contact, get separated over there, and the other carrier won't be able to recombine over here, and instead would get pushed back to the other contact where it will get collected. And so this is something where that the silicon community has done very well, and some of the most efficient silicon solar cells have been made this way. So we did a lot of work on this area. Again, I don't want to go through all of it. Most of these results on open circuit voltage are also unpublished, but we have found some evidence that TiO2 and NiO may be reasonable contacts. There is more room for improvement over here, but we have seen that to some degree TiO2 as a N and NiO is somewhat P contact are useful with WSE2. If you go and make a structure or a device like this, we have seen in preliminary data that the open circuit voltage can go up to 700 millivolts. Now, this is, of course, close to open circuit voltages of silicon solar cells. So this is very promising. This is also, if the band gap is 1300 millivolts, 700 millivolts is, more than 50% of the way there. So we feel very good about it. But then if you look at the currents over here, the currents are terrible. This is because these contacts or these transparent conducting contacts are quite resistive, and again the interface is not perfect over here, so they are leading to a lot of recombination. Further, the fact that if you look at this curve, there's an S-shaped curve over here, there's a clear sign that there is some kind of Fermi level pinning going on at one of the contacts. We haven't still figured out where, but there is a lot of room for improvement in terms of contact engineering as well as interface engineering of the contact. Okay, so I would like to speed up a little bit because I'm running short of time, but we have done similar work with another type of contact, this time a smaller gap semiconductor. This is in collaboration with Hu, where we have used arsenic phosphide alloy as a small gap contact MOS2, and where you can get nearly a unilateral depletion region because arsenic phosphide has a much higher carrier density, much more heavily doped. Most of the depletion region is formed in the MOS2. And then I'm going to skip over this real quick, but you can actually get photovoltaic performance where you can get fill factors of about 50 or 0.5, and power conversion efficiency approaching 9%, at least under 10 cents, right? And still it is concentrated power, but you are able to see both open circuit voltages reach about 0.6 volts and power conversion efficiency reach close to about 9%. And so this is again more promising, and we think that there is room by contact engineering to sort of push this even forward. So I'll say that the voltage is sort of approaching that of silicon solar cells, but concurrently I think we have to balance this current and fill factors, as well as some optical design is needed, because none of these devices that I showed you in the past couple of slides have optical design into it. And so there is room for improvement for doing all of these things together. And I'll say from my personal experience of all the unpublished data, that it is difficult to engineer all these three aspects, which is light trapping, current collection, as well as contact engineering or voltage engineering all into a single device. It's a really hard challenge. Okay, so with that, I would say that, we have made major advances towards all these three major aspects that I told you about, though combining all of these three into a single device is quite challenging. And there is a lot of room for, I think, improvement over here from the community. And I hope to see more exciting results sort of come out moving forward. So moving forward, I think there are a few sort of important questions to answer. One of question would be, what about monolayers, right? Everybody's excited about TMD monolayers. Why are you talking about all these few layer cells? The answer is that it's easier to play with few layers. And I'll tell you what are some of the problems with monolayers. Monolayers have an obvious advantage that they are direct band gap. Of course, gallium arsenide solar cells are more efficient than silicon. One of the main reasons is that they have a direct band gap, right? You can definitely make them more efficient because they have a direct band gap. You have less non-radiative losses because of the indirect band gap. The problem with monolayers is that trapping light becomes much more harder when you have just less than 1 nanometer thick active layer. And we have proposed some strategies of how to trap light in monolayers. Of course, multi-layers I already showed you. We have also done some more cool work on multi-layers and light trapping in different ways that I'll briefly talk about. But then in monolayers, there are also strategies where you can start trapping light. And the good news is, in the last couple of years, people have already published in these areas where people have shown very high light trapping in monolayers. And even we are working on some of these results over here that we'll publish in the coming year. And so I don't think light trapping in monolayers should be a problem moving forward. The advantage that you get from monolayers is clear, is because they are direct band gap and they have higher external radiative efficiency, they can be much closer to the ideal limit. Okay, and therefore they can occupy the space over here. The problem though is that monolayers have larger band gaps because they are, of course, more quantum confined, so they are at a different part of the energy spectrum over here, right? So it would be it is clear that the range of efficiencies that both bulk and monolayers occupy on this plot are sort of similar. But monolayers have another very big challenge that people don't often talk about. Okay, and this big challenge is that the exciton binding energies are really large. And therefore, you will have to spend a lot of energy to actually separate the exciton out. And this would be a huge penalty to be paid in terms of voltage that most people are still ignoring, and a lot more work needs to be done there. In fact, people who have worked in the field of organic photovoltaics, they'll know how hard this is. So one way to go about terrestrial applications of 2D semiconductors is actually see how you can pair it up with silicon. Again, just like microelectronics, silicon is here to stay even for photovoltaics. The question is, what can you put on top of silicon to sort of make it better or improve the efficiency? And so if you look at the record single junction silicon cell, of course, there is a huge push to integrate 3-5 semiconductors such as gallium arsenide or gallium indium phosphide on top of silicon because they are very well matched in terms of band gap to give you the maximum efficiency of this tandem cell. Bulk TMDCs are not very well band gap matched. Okay, plus they are indirect, so it doesn't help much. So they're only going to give you modest improvement if you combine them on top of silicon. But monolayer TMDCs, they are actually very well matched in terms of band gap. And the fact that 2D materials can be layered on top of anything, as opposed to 3-5, which are difficult to grow epitaxially and high quality over arbitrary substrates, you may have some opportunity over here in terms of integrating TMDCs in tandem cells on top of silicon. This is also one of the main reasons why solution processed perovskites have had a huge advantage in terms of integrating on top of silicon. They don't need to be epitaxially grown in high quality like, say, gallium arsenide or gallium indium phosphide. That's a big advantage. So if you look at the current perspective of where sort of the devices are lying and where the community is, the monolayer devices are still pretty bad. They are in the sub 5% regime. Even their external quantum efficiency is not very good, just because they are not absorbing as much light and not much light design aspects have gone into it. Multi-layers can absorb a lot more light, so they can have a higher external quantum efficiency. But then again, open circuit voltage engineering has not been done for them, and therefore they are sitting over here. My sense is that in the coming years, these two will be taken care of very well. In fact, I can tell you there are unpublished reports where people have been seeing very high external quantum efficiency. So this is not that hard to take care of. The harder thing to take care of is materials and interface control. And this is where, even if you are able to get very high external quantum efficiency devices, the power conversion efficiencies are going to stay low unless we work hard on, say, on the open circuit voltage. I have seen some unpublished reports where people have been able to engineer this and push this over here. We'll see when that comes out and what the community thinks about it. But the key research areas to sort of emphasize over here are, again, contact engineering, large area high quality growth with the 2DCC is doing an excellent job on. And then, of course, this big challenge over here is overcoming the extron binding energy in monolayers that very few people have thought about, and what consequences it would have if you reduce the extron binding energy on the absorption and optical constants. And finally, of course, the room is open for discovery of new other two-dimensional materials with right band gap values and optical constant. There may be others out there that we don't know that are better than these 4 semiconducting TMDCs we talked about. Finally, there is also some room for new fundamental investigations. I said that, a lot of people talk about sub-10 nanometer transistors. We're building sub-10 nanometer thick solar cells. And of course, you would have some interesting new transport over there, new physics of exciton transport, new physics of carrier collection, maybe hot carrier collection and things like that are worth investigating. I'll also say that we are now working on looking at hybrid light matter states such as exciton polaritons. And I did not talk about this further, but in our structures of WS2 and WSE2 on gold itself, you already see exciton polaritons form at thicknesses even below 15 nanometers, which is where this optimal absorption was. And so now we are trying to see if you do a photovoltaic measurement now, what are the kind of efficiencies or external quantum efficiencies you can get from an exciton polariton peak versus just an exciton peak, and does it have any fundamental consequences in terms of light harvesting? So there are a lot of interesting things to do over there in the coming years. So with that, I would like to end, and I would like to acknowledge a bunch of people, a bunch of my group members who work very hard on some of these topics, some of my former colleagues and current collaborators, including Harry Atwater, Arthur Dawoyan, Veda Hu, and a bunch of other colleagues and collaborators at 2DCC, Penn, and various other places, and of course the funding agency. Northrop Grumman is the company who would be who has been interested in looking at very thin photovoltaics, and there is also some interest from the defense agencies on that. So with that, I would like to thank you all for your attention. Sorry, I'm a little bit over time. I'm happy to take any questions.
Thank you, Dr. Jariwala. So queue up your questions in the chat box. We will not use voice because we don't want to accidentally interrupt the feed. So I will take them up to Dr. Jariwala. Okay, we have a question already. Have you measured power efficiency as a function of time? How are you trying to prevent the oxidation of TMDs over time? And then encapsulation with other 2D materials is a question.
Okay, great question. We have measured our cells, especially with the ones with high EQE and power conversion efficiency, about 3 to 4% over a course of 6 to 8 months. We have seen less than 5% variation, 5% from the day one variation. So they are relatively quite stable. How do you make them stable? Well, we have mostly used sulfides and selenides from Scotch tape crystals, which are naturally quite stable materials. Further, if we have also tried to put a layer of BN, a thin layer of BN on top, and that seems to encapsulate things pretty well for a very long time. So yeah, this is certainly the way to go. I think to prevent oxidation, you would have to cap it with something, and there is also optical design to be done in capping layers. Like if you have a higher index sort of capping layer, you will end up trapping even more light. You can also use other 2D materials to do the same.
Okay, what happens in space? The spectrum changes. Does this change your ideal choice of TMD? And what do we know about UV tolerance?
Great question. Once again, yes, we have thought about it. The good news is that, and there were some preliminary measurements done right before I left Caltech at JPL to look at radiation hardness. Actually, the biggest advantage that you get because of the very small thicknesses is actually these cells are much more radiation hard. And so the space radiation, right, and high energy radiation, and that is actually beneficial in terms of putting it up in space. In terms of spectrum, not much changes. Actually, the intensity changes more. The spectrum changes more on the IR side because the atmosphere mainly absorbs the molecules in the atmosphere, they mainly absorb in the IR side. So in terms of visible intensity, the overall intensity goes up, but the actual spectrum does not shift. Our sun's temperature, the black body temperature, it's going to remain the same whether you are on Earth or you're up in space. So it won't change as much of the band gap of the material. But there could be some other interesting things we could look at over there, such as if one material is more radiation hard than the other, then maybe that would help. Certainly having moly, tungsten, all these things are heavy elements, maybe over time they are more sensitive to, say, heavier radiation such as alpha particles, and some of the lighter element 2D semiconductors may be better over there. I don't know. It's something to be explored.
Is arsenide phosphorus a layered material? How was it synthesized?
Okay, great. I skipped over it very quickly. It's basically black phosphorus alloyed with arsenic. So yes, it is a layered material. It was synthesized using the same ampule technique, where you put in some powder of phosphorus and arsenic together, seal it up in a torch tube, and heat it up at high temperatures, and therefore, because you are sealed up in an ampule, it also becomes high pressure and ultimately grows into an arsenic phosphide crystal. This was actually grown by our collaborators in China, and we just exfoliated it, and it works out fine. I think the arsenic and phosphorus content was 50-50, so the actual formula is ASP.
In the slide showing the paper from 1981, the text says molybdenum disulfide is direct bandgap. Isn't molybdenum disulfide indirect bandgap?
Yeah, it's a very good catch. And when I read the paper, I saw it too. And probably in 1981, people did not know whether it's direct or indirect band gap. The funny thing about MOS2 or any of these TMDs is that if you look at the absorption spectrum, even for indirect materials, right? So this is for example, we are. Let me pull up my WSE2 slide. If you look at this absorption edge of 13 nanometer WSE2, which is basically indirect, we know it's electronically indirect. The edge is so sharp that most people think it is direct. Right? And back in 1981, people were not thinking about we should do some kind of photoluminescence measurements or this and that to determine direct versus direct. So obviously they were they did not did not think about it that far. That's my guess. Hello. Hello. Hello.
How would turbostratic few layer TMDs behave as photovoltaic? Would they behave as a stack of monolayers?
So this is an excellent question, and I have given some thought to this. I haven't actually had my hands on a turbostratic sample to sort of measure this, but it may be worth thinking about. I mean, with this whole idea on the condensed matter side of 2D materials of trying to twist layers, if I take a few layer TMDC and twist all these layers, how does the band structure change? And I think the big question I'm trying to get to is the same as what the user or the viewer has asked, but trying to engineer a structure that will give me bulk-like absorption and performance, but having equivalent to a stack of monolayers. And we're working on it. I'm not showing it because it's all unpublished data now. Hopefully you'll see something along these lines in the coming year from our group.
Okay, and recognizing the value of your time, we have one last question. Can you project how fabrication costs will compare for these multi-layer and monolayer TMDC photovoltaics compared to silicon?
Yeah, so again, this is an interesting question, and I think you have to talk more at a economic level over here, in the sense that what is the application, right? If the application is going to be space, then the cost of the cell does not come into picture at all, right? It's the cost of shipping it up there that matters. If you are going to put it on the ground, yeah, then you have to think about it. And I guess the experts at 2DCC would know better how much more expensive it is to grow a monolayer film versus a multi-layer film. I think the challenges in terms of fabrication, aside from synthesis, would be For trapping light in a monolayer, there will be more sort of lithography-like things needed, because you will need some kind of resonant absorber or resonator to trap light, and that would significantly escalate the cost. So I think it's this cost benefit versus efficiency analysis that you have to do and see what makes the most economic sense for the application you're looking at.
Actually, we have one more question. I think we'll take one because I think it's got pretty high value. But for those of you, we're going to shut this down after this question. If you enjoyed the talk, go ahead and type the word clap in the chat box just for our sense of humor. But the question is, thanks for the talk. I assume all the WSE2, WS2 are from exfoliation, while my chat box is blowing up, from exfoliation and stacked. Have you tried to use CVD grown multi-layer TMDs to make the same structure? And how's the performance compared to device from exfoliated crystal?
Very good question. As you can see over here, we have made these films. So these are already half your cells. So definitely optically they are there. Electronically, they don't work very well. This is because, the real challenge with multi-layer films, I would say, especially over large areas, is if you're going to make a vertical device, any short through a 10 nanometer or 12 nanometer thick structure, and you're going to get your full cell shorted. So we're working on it. I can't give you a timeline like when we will have results from, say, multi-layer large area cells that you can directly compare to exfoliated ones. My hope would be that someone in the 2DCC or one of the other experts gets me really high quality multi-layer films, which have very low sort of pinhole-like type defects. I think atomic defects such as vacancies are okay, but very low pinhole-like defects. And we can make a cell and see how it looks like. So I think we are limited to a high quality hole-free material over large enough area by CVD to make a test out of this.
Thank you for your talk today, Dr. Jariwala. I'll let you know that in the chat box, just about everyone clapped. So they enjoyed your talk immensely. Some people used emoticons, so that was pretty cool. But anyway, stay tuned for next time. We don't have a next date yet, but we will use the same format for future webinars for the foreseeable future. So thank you again, Dr. Jariwala.
All right, thanks everyone.